Howdy, my name is Jian Tao. I'm assistant professor from the School of Performance, Visualization, and Fine Arts. And I'm also assistant director for project development at the Texas A&M Institute of Data Science. So I have been working closely with folks here at HPRC. And today I'm going to show you all how to do CUDA programming. So let's get started. So for today's short course, there are 4 parts. First one, part 1 will be getting you all familiar with the FASTR. I believe some of you have already taken the short course offered by HPRC, I'm not sure, a couple of weeks ago, about FASTR and ACES. Today we'll briefly review some of the specs of FASTR system and also get you all started quickly on the system. And in part 2, we'll talk a little bit about GPU. And it's kind of ironic, even though this one is about CUDA programming, I'll be spending about 1/4 or 1/3 of the time to persuade everyone not to do CUDA programming. You'll see what I'm talking about. You know, it's just a quick quote. And then part 3 is about running CUDA code on FASTR. Usually we put this in part 4, but in many cases, sometimes we didn't get enough time to get this one done. But I think it's important for everyone to get started running code on FASTR first before we move to the basics of CUDA. And then the part 4 will be about the basics of CUDA programming. And this is a combination of intermediate level of introduction and also beginning introduction that we have been organizing and preparing for our users at HPRC. I do have intermediate level slides cut it out, and I'll prepare some more slides later on, and hopefully we can share with you all. And those slides will be helpful to understand some more details about the CUDA architecture and give you some better understanding about why CUDA programming is like this and how why you do this will help you to improve your performance, things like those. So part 1, let's get started with the FASTR. And I believe some of you, or probably many of you, have already taken the short course at HPRC about FASTR and ACES. And I have a link here. If you have access to the slides, you can click the link and you get to the PDF file showing you, more information about the slides. And you can also go to HPRC website and you can find the recorded video about FASTR and ACES. And I'll briefly go through some specs, and it won't take long. And first, FASTR is a project supported by NSF as through the MRI research program. And it's a kind of different architecture, like, it's not like traditional HPC systems. So on FASTR, it's a combination of different kind of accelerators. Mostly for FASTR, mostly CPUs, and we'll talk a bit about ACES, which is a combination of different accelerators. But they are all based on liquid system, where you can define a composition of your system you want to use, depending on your particular requirements. So if you are familiar with the concept of software-defined network, FASTR is kind of like software-defined supercomputer. So I'll skip all the details here. You can get the information about more information about system. If you are a user from outside Texas A&M, there's a one login node for ACES users, and there are 3 login nodes for TOM users. So this slide more or less explains what I just mentioned about software-defined supercomputer, in the sense that we don't, in the way how the liquid system is organized, they don't have a clear definition about which node contains which processor or which accelerator. They're all put together as a big pool of servers or CPUs, a big pool of accelerators, GPUs, FPGAs, etc., and a big pool of SSD. Depending on your job and depending on your requirements, you can tell the SLURM, which is a resource management or job management or queuing system, depending on how you call it. So it helps the user to define the particular resources they need for their particular job, and then the system, the queuing system, will talk to the management system that Liquid is providing. Liquid is a company which is providing this solution. So Liquid software will figure out how to combine all the hardware together and provide this software virtually to you, to the queuing system. And the queuing system will get this back to the user, and the user can use whatever resources needed for their job, which is a pretty neat idea. And it's a serves, the resources and make it more efficient and maximize the usage. So ACES as another big system supported by National Science Foundation, and it's a multiple-year project, I believe actually 5 years. And the goal of this project is to accelerate computing for emerging sciences. You can consider this like a test bed for accelerators. And it's one of the innovation systems that NSF has been supporting, even though the total capacity of this system might not be big compared to the capacity systems that NSF is supporting. It contains a lot of new accelerators that you cannot easily find anywhere else. And here just we list some of the components here. The graph IPU is something we have been testing since before the project got funded. We have been working with the graph core team to explore their IPU systems, and also Intel FPGA, and you can log in and try things out. So this is just a phase 1 for ACES system, and in the phase 2, and when the system is in production, you can have access to more accelerators, and we'll be gradually adding more different kind of accelerators for testing and development purpose. So also the phase 1 components are available through Faster. You can look into the details on the website. To get access to Faster and future ACES, you can use our portal. And as you can see, there are 2 links for Faster. One is for local users, another one is for ACES users. For local users, after you log in, after you click the link, it will point you to this login page, which requires your TAMU ID. And that's a local credential you need to get authorized to get access to the resources. For ACES users, you need to log in through the newer ACES authentication system. That I'm new to the system myself. I am used to be an ACES user. It took me a couple of minutes to figure it out, but after you get access to it, everything else should be straightforward. You need to enable your dual authentication and other things, and then everything else will be working in a similar way like other systems. So first, let's try to, now I believe this is, let's try to use this Faster system for local users. I'm sorry for ACES users, we'll go back to the ACES portal in a second. We'll start with the local users. After logging with your TAM credential, and you can, so after you get logged in with your TAM net ID and credential, you should be able to see this interface. And here, if you click clusters, you can see there's a Faster shell access link. If you click it, it'll point you to the slide, to the page to the left here. You need to type in your password. That's your TAM credential ID. And then you need to use your dual authentication to authorize your access. And then you'll see the prop to the left here, which is the screenshot I took with my current quota and other information. So I'll not wait. So I'll just continue with this while you're listening to me, because in the first part of this slide, of this short course is very, very generic description. You can, while you're listening to me, you can try to log in, type in password, and wait and do something about it. So I'll continue with the slides. So the command to copy examples, we'll get back to this a bit later, but I think it's good for you to have access to the slides so that you can copy paste this command line. Sometimes it's longer than that you can comfortably typing. So the best idea is that you first get to your scratch space. That's the scratch space that we want everyone to run their code. You don't want to use your home directory. Mainly in most systems like this, the home directory is kind of small, and we encourage our students, our users, to use a scratch space. You copy the data or copy the exercise and examples over to your Squarespace, and then you unzip it, and then you can just cd that directory and continue doing the rest. So it's a standard way to get the file, copied over, or you can use a wget to download directly from the HPRC website. So you can easily copy this and get it downloaded and unzip it, and then cd the directory and wait for the next step. Or you can start trying something out yourself. So that's all you need to do, get prepared. To run as an NVIDIA compiler to compile your code, you need to first load the module. So currently I'm using a shortcut ML, which means module load. It might not be the same for a different system, but that's what we have been using here on our system. It's working. It's easy to remember, module load ML. So CUDA here refers to the latest CUDA version installed on our system. You might, if after you get familiar with our system or get familiar with your application you want to work on, you probably want to choose a certain version of CUDA. So this might not be the good solution for most users. You might want to get ML. You want to let me hide my. You want to probably want to specify a particular CUDA version to load here. And you'll see one example in the job submission script. So after you get that loaded, then you should be able to see MVCC directly. MVCC will be in your path. You should be able to directly run MVCC. You can compile it, you can run it, and you get something printed out. So that's already sufficient for you to start running something non-trivial here, and we'll get into the details in the rest of the short course. Before I get into part two, any questions here for the first part? All these should be straightforward if you're familiar with the system. If not, you might want to get back to some other short courses offered by HPRC or some other collaborators on ACES, collaboration, and you want to, get yourself familiar with the system first. So I'll not spend more time on this one here, but feel comfortable to ask our staff members if you need any help to get access to the system and get started on our system. So this part is trying to explain what a GPU is, and to most of us, I'm referring to us as the programmers, computational scientists, engineers, we use GPUs as accelerators. Of course, you can use it for play games and doing all other things, but as in the context of this short course, most of GPUs are used as accelerators. That's what GPUs are designed for data center servers. So compared to CPUs, a GPU are accelerated in the sense that you cannot run operating system on it. So the CPU can handle very complex logic. You can run an operating system on it. You can manage your whole system. But GPU is taking a different design approach. It was designed as an accelerator. What it does is take what data provided by CPU and process and get it back to CPU. So that's what GPU have been designed for. But of course, if you go to AMD and NVIDIA website, there have been plans and discussions. You'll see some blogs about those companies starting designing the CPU GPU together. There have been a lot of effort. AMD already have something out, and NVIDIA is working on that. It's not a secret. So with the GPU and CPU together, you may imagine a lot of things we will be talking about today might not be that so important. For example, the data communication between CPU and GPU. That will be a big problem for CUDA programming if you want to maximize the performance. And you'll learn a bit more about that today. So NVIDIA has been dominating the market as far as the GPU itself is concerned, and it has been doing very well with their design and manufacturing of this high-tech chip, which is, I think, the driving force behind AI and machine learning nowadays. Almost every big vendors who is doing AI and machine learning, they use GPUs. I would say 90% or even higher than 90%, based on some latest market survey. So the one I'm showing here to the right is the A100. That's accelerator we'll be using faster. As you probably heard, NVIDIA they released the H100 Hoover, which is a newer generation, but we don't have those here. Probably we do, but that's even we do, it will be a testing case, but it's not something we can use right away. So this A100 we have on our system contains 54 billion transistors. That's a lot of transistors you can imagine, and it has a pretty high memory bandwidth, and it has a lot of memory. Just for the chip itself, the GPU itself, the big one, there are two, as you probably know, there were two versions. Actually, more than two versions. Actually, as far as the memory is concerned, there was a 40 gigabytes A100 and 80 gigabytes A100. They have designed this for PCIe interface and SMX interface. So, totally, if you put them together, 4 different combinations for A100 different models. So, why do we want to use a GPU? One of the major reasons is that GPU is power efficient in doing a lot of calculations. I just put some number here. These are some older slides, so don't worry too much about the efficiency here for the Jaguar. But after the upgrading on the Jaguar system, there have been dramatically improved the performance and also the power usage. But this is probably the very first version of Jaguar when this is up and running. It's one of the supercomputers. If you visit the top 500 list, you can find the name here and find some historical measurements. So the reason that GPU can be so efficient mainly because GPU, the design of a GPU is actually simpler than CPU in a sense that every core is designed to handle simple tasks. It's not like CPU. You need to deal with different, logics, and there are more complex design in the chip itself, so make it not so power efficient as a GPU. With the GPU accelerated computing, it's more or less like a new era. That's actually the beginning of the AI and machine learning era in a sense that with all the GPU power efficient GPU computing power, and a lot of data readily available, you can train more efficient models, more powerful models to drive the AI and machine learning development. So the GPU computing applications could be divided into multiple groups. If you look at the very top, you have a GPU computing applications that you rely on the libraries, middleware. Those are highly optimized by NVIDIA engineers and also third-party providers. They work together to provide those highly efficient libraries. Underneath, you have programming languages, C, C++, Fortran, Java, Python wrappers, and OpenSEC, and now OpenMP also supporting offloading the computing to GPUs. And you have a CUDA-enabled NVIDIA GPUs. There are multiple generations, starting with the Tesla S1070. No, actually, that's even, there are some models even earlier than that. And nowadays we have H100, which is the flagship GPU card that NVIDIA is producing. But of course, there are many other different manufacturers. But today we are focusing on CUDA, so we don't talk about other GPUs for this short course. Okay, this slide shows a very, very high-level overview about how GPU works. So without GPU, that's just a regular computer. I'm talking about NVIDIA GPU, discrete GPU. If you have a computer without discrete GPU or NVIDIA GPU inside, you will be mostly using the embedded Intel GPU, which will be sufficient for you to handle a lot of graphics and handle a lot of graphical needs for your application. But when you're talking about general computing, CUDA and the CUDA-enabled GPU by NVIDIA, it's a working horse for GPU-enabled computing. So the basic idea is that you have application code. The majority of the code, or the main process of the code, it will be running on CPU. But there will always be some computing intensive, or we call it bottleneck, that when you run it on CPU, this part will mostly take, probably majority of the time. So identifying these bottlenecks is actually the very first thing to do when you start looking into porting existing code into onto GPU. And after identifying this particular section of your code or particular function, you can try to see if you can offload it to GPU. If you can, then a big chunk of your data, will be transferred to GPU, and a lot of computation will be done on GPU. If you do it right, you can speed up your application, and you can greatly reduce the computing time. And of course, there are many other constraints like Amdahl's law. If you are not familiar with it, it's okay. So what it tells you is that there are always a limitation about how fast you can go. The fastest, the maximum speed up you can get is fully determined not by the green part here in this diagram, but by the dark blue parts. Just imagine in a optimal case, when your GPU can run, instantaneously fast, much faster than your CPU. So the time taken for the green part to run is just 0 in the ideal case. Then your total time is fully determined by the part you cannot optimize, right? So sometime if you want to look at look at some problem to port your application to GPU, you should have some idea about what's the maximum you can do, because in many cases, those dark blue parts of your code probably it will never leave. You cannot accelerate those with GPUs or any other accelerators. So the total time saved could be easily estimated, actually. So that's actually the very first step when you start looking into porting your code from CPU to GPU. And there are a lot of online instructions and tutorial about how to do that, but we'll not focus on this porting part. We'll just focus on the CUDA writing to get started. So this slide shows a general overview about how all this current distributed heterogeneous system are working. Consider each node here is a regular node. This is not a faster system, but it's a node that you can have accelerators. You have multiple cores in your CPU. You have memory that will be shared between your accelerators and your CPU, and then different nodes could be connected together through network. The faster is kind of different. It's mixing up all the communication by using the PCIe generation 4, and I'm not sure if they have version with the generation 5 yet. So with the PCIe, it's like using technology. If some of you heard about external GPUs, you can connect your GPU through PCIe through the pretty specified port. If your laptop supported, then you can have a pretty decent laptop. Without the switch GPU inside it, you can connect directly to external GPU, and you can do a lot of fancy graphical stuff. I know a lot of Mac users are using eGPU. So the idea is kind of similar for faster, is trying to support the communication, faster communication between all the computing devices using the PCIe generation 4 communication mechanism. But I'm showing here is like a distributed heterogeneous system, which is like a traditional way of doing that. We use a high-speed network to enable communication between two nodes. The traditional programming model is just MPI plus something. Could be MPI plus CUDA or MPI plus C plus CUDA. Then you have a C to manage the main processes, and you have CUDA to run the GPU-enabled part. So for the CUDA parallel computing platform, there are multiple levels. You have a hardware part, you have open compiler toolchain, you have development environment, you have programming approaches. So today we'll be focusing on 3 programming approaches at the top. So the very first one is to use libraries. The libraries, as I mentioned, those are highly optimized by NVIDIA software developers, and they have access to the latest development in the hardware. They know exactly what they need to do. And I don't think any programmer, if they're not affiliated with NVIDIA, can easily beat them if you just look at the performance, mainly because they have all the things they need to know. And also the CUDA architecture itself, even though it's open architecture in a sense, it's open to all the external applications, but inside they have a proprietary codes that are not shared with the community. and I'm not saying the CUDA itself, I'm just saying the libraries and the drivers, and which will be dramatically impact the performance if you want to fully leverage the hardware, computing potential. So for libraries, the benefits, it's very obvious. It's easy to use, it's dropping, and the quality is very good, because no one can beat NVIDIA in writing, NVIDIA libraries, right? So the performance also, it's almost guaranteed. It's tuned by experts, and it's always hard to beat the performance for NVIDIA libraries. So there are many there because NVIDIA knows their advantage. So they have been pushing hard, developing a lot of software for the community, and some, I believe most of them are freely available. There are some very specific applications that is still, either it's still under development or they haven't really opened it up yet. But most of the libraries that are usable by engineering and scientific community could be accessible through the NVIDIA website, developer website. So this is one example how you can easily use Cuda libraries to speed up your application. For example, if you want to do a linear application about x plus y, that's sx plus y. Basically, is what you're doing is x plus y. That's what the function is trying to use, trying to solve. And the easy way to do that is just replace the function name from sxpy to CUDA plus sxpy, and that's it. So the same argument list, same parameters needed. You don't need to change anything in your argument list. And the second step 2 is to make sure you allocate memory on the GPU, because the sxpy is using the CPU to do the calculation. So all the variables, arrays, and other structures, they allocate memory in the main memory. That's where the CPU have access to. And now if you want to run it on GPUs, you need to make sure you allocate enough memory for the library to use so that you can run it on a GPU. So we'll talk about this a bit later, about memory allocation on GPUs, because that's an important part for CUDA programming. So let's just look at this whole steps. First, you replace the function name, and that's it. Just function name replacement. And then you allocate memory for your variables. Also allocate memory for some temporary variables used by CUDA Plus library. And then you rebuild it, and that's it. So by doing this, you can directly use the CUDA enable library on GPUs without doing much coding. You don't do any CUDA programming here. You are directly using the CUDA accelerated libraries. So the reason I think this is a very good way to probably the way to go in the future, because there will be more and more similar libraries, being compatible with the CPU version. And you should be able to do this without digging into the details about how to do the CUDA programming, which is, easy to get started, but harder to work and, develop a real functional or highly performance CUDA code. And that's my take. And I would call myself experienced CUDA developer. That's my take. If you can, try to use libraries. So that's probably your best take. You can get max performance with much less work. And it's the best way to go. And there are many tools on the NVIDIA website. You can get started looking into some existing libraries to see if you can quickly replace your existing ones. If not, try to see if you can change your problem to reformulate into the way that CUDA libraries can use, and then you can do that. That's still much easier than starting from scratch with a CUDA code. So the second approach is to use so-called OpenSEC directives. Directives, I'm sorry. So there are, so the OpenSEC standard has been there for a while, and it's kind of very, very similar to OpenMP in many, many ways. If you are familiar with OpenMP, you can compare that OpenMP with OpenSEC. You can see there are many similarities. You need to define some pragmas to tell the compiler, hey, this is a loop I want to parallelize. You tell very specific looping conditions. There are many other things you want want your compiler to understand. But what you're putting in your code is nothing more than some comments. So all the comments are there just to tell the compilers, hey, this is a part that more or less like it's a loop, and I want you to handle each individual calculation for each iteration separately, because if if all the loops, each loop doesn't depend on each other, if you're just iterating through from one grid point to another grid point, and each loop, each iteration doesn't depend on others, those can easily be optimized, can be easily distributed to different cores or different computing units. So OpenSEC itself it's very easy to get started. It's open in a sense, it's open standard. It's not NVIDIA. Even though NVIDIA played an important role in getting this OpenSEC standard started, and it's still supporting OpenSEC in many ways. And it's very powerful to get you started, to get something running without writing a single line of CUDA code. Okay, so that's another way. And of course, there's no free lunch. OpenSEC has many limitations. One of the limitations is that it's not so flexible. If you want to fully explore the computing power of your GPUs, OpenSEC is not the way to go. It's based on some very ideal computing model. And if there's any complexity in the way how the computing is doing, OpenSEC will not work. If you have a lot of if conditional statements, of course, CUDA will not work nicely in this way either, but at least you have some way to tweak it or make it work probably a bit faster. But if you're using OpenSEC, and if your code has a lot of complexity in the logics, you'll get stuck. There's no way you can easily use OpenSEC to make things happening, faster than what you can do with CUDA. More or less, like CUDA is give you a very, very low level toolkit for you to do things in a more flexible way. And OpenSEC give you this pattern that you can apply, but this pattern might not be working everywhere. It's just very generic patterns for doing the data parallelism and also task parallelism, but it might not be working in some special cases, or it's kind of hard. You spend more time to tweak your OpenSEC pragmas than just writing your CUDA code. So again, this slide shows you some successful stories, but it's not always like that. That's my take. Okay, that's enough. People will have to OpenSEC people will hate me about it. So lastly, about programming language. So of course, it's giving you maximum flexibility. But again, if you are new, and actually, if you are here, listen to me talking about the beginning of OpenSEC, beginning of CUDA, and if you are planning to work on some big project, I would suggest you probably look into the libraries. Learning CUDA is if you have any programming background, especially C and C++, it's straightforward to learn to write code in CUDA, but to optimize it and to make it really work for your application, unless your application itself is not that hard, then it might be a nightmare for you. It just takes too much time to get a real high performance CUDA code working. That's a good question. Actually, yes. So that's actually some of the things I have been trying myself. Basically, you mix libraries and OpenSEC. So you can, depending on the complexity of the problem, and you definitely don't want to use OpenSEC to wrap things up to solve some very, very specific problems. You probably want to use a library to solve the linear equations. You don't want to write your own OpenSEC code to solve these linear systems. So it's like a mixing of different things, but also depending on how your code is structured. If you have a multiple hotspots in your set blue, I have showed you all. You have green ones that could be accelerated, and the blue ones cannot be easily accelerated. If you have multiple blue blocks spreading around your code, then some part of that could be replaced with libraries, and some part of that could be easily done with OpenSEC. So that's probably the way to go. And also, OpenSEC you can use OpenSEC to call these external libraries as well. So it's like a mixture, like an embedded way to write OpenSEC code and library code. So that's, I would suggest, probably the best way to go to get started first. And then if you really want to explore the maximum performance and maximum flexibility, CUDA is probably the only choice. So these are some programming languages that you can use to write a CUDA code, and there are some of them might not be actively supported, but I just want to keep them here. There's one I'm from the Java version, Java ramp for that. CUDA Fortran, even though it seemed to be working, but I don't think so many people are using that. And also, let's see what else. And the CUDA Pi, even for Python version, there are two versions here: there's PyCUDA and CUDA Pi, and both have their advantages and disadvantages. You can look into those and decide if you want to try them out. So Thrust is another interesting development framework. You can use that to wrap things up that can work with both CPUs and GPUs. I just show one example here. I will not go into details. If you are interested in looking into some programming frameworks that can work on CPUs and GPUs and potentially FPGAs in the future. Probably it's already supporting FPGAs. I haven't looked into Thrust lately, but it's not just working. Sometimes you worry about not just porting the code from one accelerator to another accelerator. You're worrying about the performance portability. You want this code to be run faster and faster with even better, more decent accelerators. Performance portability is a big concern, but getting code portable across multiple devices, it's now doable, through many tools there. But performance portability is a big concern. Thrust can probably help you with some of those, so I'll leave you all to some experts on that perspective. So there are more information you can learn from all different languages. They are supporting, they are supported on all CUDA-enabled GPUs. Okay, let's get back and get started. I believe it's 15, right? I just want to make sure I didn't get the time wrong. So, as I mentioned, usually we put this towards the end of the short course, but I think it's good to move this a little bit earlier so that we can get everyone some experience with faster before time runs out. So the very first thing you do after logging faster, I assume you all can log in faster. If not, I'll give you some time. I'll show you how I get logging faster on my end, and you can see probably we can do all this together. So this is what I will do. I'll go to HPRC website. Can you all see my screen about the website? Jinhua, can you see that?
Yes, we can see.
Yes.
Okay, great, thank you. So I'll use my I forgot which one I have. Let me try one. So it's logging me into our portal. If you go to clusters and faster shell access, it'll ask me for my password. And then now it's a dual authentication. It's good. I can approve it on my iWatch. So it's empty. I have nothing here. So based on what I showed you all previously, you can see right? You can use a tab to finish, to autocomplete. So you can type in $, dollar symbol, and SCR, and use the tab. It will put you on, move you to your screen space. So I already have my files here. Let me remove them so that I can okay, so we have this. We need to go back to the link is hprc.tamu.edu. You can directly go to the website. So you can either directly download the file from our website using wget, or you can use copy from the scratch. We have this in the training directory. I believe it should be the same, but I think let's do this way. It's probably more systematic. Download the file. Let me, it's fine. I can just tar zxvf CUDA. It will unzip the file into CUDA directory for me. So I have these three folders contain 3 different examples. I also have this job script. For some reason, this job script is showing me the whole information. Let's see if so this web-based terminal is not showing the rest. I'm not sure how many nano. If you are not familiar with, or you can use a nano. Well, nano is the same problem for some reason.
Try putting a backslash in front of the VI. Go ahead and exit Nano and put a backslash in front of the VI.
Control Z. Interesting. I never use a backslash.
Yes, please.
It's you say in front of VI?
In front of the VI. Backslash. The other slash.
Will this work? Backslash.
That's no, yeah, that's it. Yes, try that.
Ah.
Now you've got nothing. No.
But interesting. It's happened to me with this web-based interface, but with the terminal.
But Dr. I think you can use our file editor on portal. If you go back to the portal,
yes,
and you go to files.
Yes.
And you have files, and where did you see? Yes, and
It's
then you can go
CUDA.
to the CUDA, yeah.
Right.
And then
That's
you
correct.
can click on it, and then do you see the triple dots? The triple dots
Yeah.
on the right. I think maybe on your left.
Yeah, I can see.
Yeah, and
because
then you
edit.
can edit. Yeah.
Ah, I never use the portal this way. I usually just log in with my my shell and do everything was there, but sometimes it's not working. It's just probably on my Mac. I tried it on my Windows and my Linux system. It's working. I don't know what's the problem is. But you can take a look at this job script that Jin Yuan and others they have been helping me to make sure all these ones are matching with the current setup. I believe the part you're modifying is this one, right? It's on the particular particular node. These are the reserved for this
I guess no. Maybe you need to re-download because we made some updates to use the T4 GPUs.
Okay, so this
and also
T4.
Yeah, T4 GPUs. And okay. For T4
I see. So
GPUs.
I probably better for me to just copy the other one instead of using you can use a clear. I can use CUDA exercise, CUDA, and then copy the one from the website. My slide, I'm sorry. So this is probably the best way to go.
Yes.
Okay, sorry about it. So use this one, don't use the other one. This one has been updated to reflect the changes. So I copy this to my scratch space, and then I can unzip CUDA exercise. Okay, let me go back to the, I needed to leave. So this should be, let me refresh this one to make sure. Okay, so I can use this to do the editing, which is, yes. So if you all can see, we are using T4 here, reserved for this short course, and we can, after we submit the job, it can run directly. Otherwise, we'll be put into the queuing system, waiting for a long period of time before the job got executed. So another thing I want to mention here, as you can see, for this job script, I use a very specific CUDA version, 11.7.0. And now, if you do the module load CUDA, it will be loading the latest version. I believe it's a 12.0. And we can double check that. This is probably the more reliable version. At 12.0, it's relatively new, and sometimes some code might not be working properly. But for our simple testing cases, it's not a problem at all. So all the others, you can probably, keep most of them the same for your job, but just in some cases, you probably want to choose what node you want to use, and then depending on the particular queue and also how busy the queue is, your job might be executed right away, might be needed to put in the queue for a while. If you're using what I believe A100 should be very busy if you want to use A100, because a lot of people using that one for training jobs. And T4 and other nodes are relatively, people use that for inference and probably smaller jobs. Okay, so that's the script. Let me go back to the shell. So we have the shell here. And let's go to hello world. I use a tab. Again, if you're not familiar with Linux, you can follow me using tab key, and it will be very straightforward. So now, if we do ML, it'll tell us nothing is loaded. ML is equivalent to module load. It's the same thing. So nothing is loaded. And I'll be loading CUDA. So this is probably the simplest way. So I can do ML one more time. It shows me CUDA 12 is loaded. So this is the default version. If you are not specifying any specific version of your CUDA, and it will load the current latest, probably the latest version that you have. Now, if you do NVCC -- version, this will print out the NVIDIA compiler that tells you about particular version numbers and also the other information. Okay, so when I log in any GPU nodes, the first thing I want to find is what kind of GPU I have. Now there's one, I'm not sure if I want to show everyone here, but never mind, I'll skip about that. So let's try to do the NVCC hello world. We can compile the host code. I'll show you what this host code looks like in a second. If you don't specify -o here, it will output everything into a.out, which is a standard output used in in the Linux community. It's a standard output for C and C++. If you don't do that, if you compile it, it will create a.out file for you. So that's if you don't do a lot of production level code development, it's easy to just for you to use this as a standard testing name. So when you run it, it will print out the hello world for you. So let's look at what this code is about. So what it does is which sense? Probably it's also skip. Let's go back to the editing file. Let's go to hello world directory and check out this host file. Let's do the view here. Oh, it's actually it's not cheating. So it's the same. Where's my okay? Let's do the editing for the host. So what it does is it does nothing other than just print out the hello world. It's just a standard C code. If you're familiar with C or C++, this is a standard C code. Okay. I think there's some questions here. I'm sorry, I probably missed that. Okay, Zhenhua, thank you. Let's look at the other one. So this is a CUDA code doing something non-trivial with CUDA. What it does is it defines this kernel, which is a dummy function. It doesn't do anything. If you are familiar with C, it's just empty function. So, but my main function does have this very strange statement. And we'll talk about this one. It's called a kernel launcher. It's trying to launch this kernel on one thread. And then it will print out hello world on the host code. So the GPU doesn't do anything, but it does launch a kernel. So this action should be activated. So actually it does try to launch something on the GPU, even though it's a dummy function, but it does something. So let's go back to the code. So we can do the same thing. It's just NVCC hello world device. And then you can a.out. Of course, if you want to give a different name, just -o, say device. So there is a file called device generated, but it's your choice. Let me just remove. Now, if you want to run it on faster and submit a job to run it. So I do have a file created. I already showed that. You can copy faster. ... means the parent directory, and then to the current directory. You can have this file here. And then we needed to compile it because in this file, I'm trying to run a.out. So we needed to compile a file. Let's do another compilation. Device. So this will create a a.out file. If you go to editor, let's go to the online editor. So let's refresh it because I just copied the file here. As you can see, it's not showing up on my current directory. After I refresh it, you can see the shell script pops up. Then I can edit. So as you can see, after I load, module purge is a very good practice for you to purge out any any preloaded modules to make sure you have a clean environment. And then module load CUDA will load this particular version of CUDA to your current directory. So your environment knows where to find the CUDA compilers, where to find the CUDA libraries, where to find all the relevant, third-party libraries and header files, etc., for compilation purposes. And then you run your program, and that's it. So that's what this job is about. So all the above, if you're familiar with shell script, all these are just comments. So technically, you can directly run this script on your node. So all the things I highlighted here with all the pound sign here, those are just ignored by the shell. So it will directly run and these 3 lines actually: module purge, module load, and a.out. And so just to show you how it works, let me go back to here. So if you are familiar with shell, you can directly run this as a shell script. So what it does is simply just run your a.out. Now, this basically run this script on your node that you're logging. So that's your login node. We want to run this job in the background, and we want to submit this job to a computing node. And we can do s-batch. That's a Slurm command for you to submit your job. And this. So it's fine, don't worry about that. If you want to know if the job got submitted, you can see this is my job got submitted. I'm not sure C is canceling, but it's fine. I got a job submitted. I know some others might be using the same name. Try to rename it. I made a mistake previously when I tried to share this job script. I keep my email address inside my job script. So when 20 or 30 students or attendees for the previous short course, they trying to run this job, everyone's sending me an email about the job got executed. So that's some stupid mistake I made before, but this time I just commented out the line just in case someone forgot. So after the job got executed, if you notice, that's my job ID, which is 1527556. I have this job ID here. Standard out, it's when you don't specify any output, it just output whatever print out to the screen to your file, and with the job ID and the extension of that file. Let's see if we can see this file here. If you print it out, you can easily do this. Okay. They'll show you hello world. That's what actually it's inside this file. That's what your program is supposed to be outputting. Basically, we successfully run this job on the front end. We also submitted a job to the back end. It runs on one of our GPU queues. If you want to look at the queues, there's a S-info here. You can look at all the queues available. I believe we're submitting to, I'm not sure which one. Let me minimize the window a little bit. We submitted to a GPU queue here. And then we are using a very specific several specific nodes, T4 nodes on the GPU queue. So as the info print out the information about all the queues available on the system. If you want to try the FPGA, run it on FPGA. And the staff queue is a special queue for staff members for testing and other things. So if you're not staff member at HPRC, don't submit a job to that queue. Of course, it doesn't hurt. The example shows two different versions, but rather to use consistent version, I think. Okay. Yeah, so that's a good question. So when you try to compile it, you are using the, I'm using CUDA 12. And in the backend, it's loaded with the CUDA 11.7. But for these simple cases, it doesn't matter. But if you are using different libraries, there might be some backward compatibility issues. You'll have problems. So it's not a good practice for me to just share an example like this. But I think it's a good example for you to learn. Actually, you see what mistakes we are making, right? Thank you, Zhenhua. So it's a pretty common mistake. Sometimes when you get your front end, you load a different version of CUDA, you compile it, and when you run on the back end, but you're loading a different version, your code will crash and produce some weird errors. And sometimes it's very, very hard to debug those kind of problems. So it's good that the one of our attendees pointed out, and let's be careful about what particular version we have. In most cases, simple cases, if you are not using very specific features, in a certain version of CUDA, it shouldn't be a problem, but just in case. Okay, I think that's mostly about this. So this, I just trying to get you all started on the examples here. And if you can run through all this without any problem, congratulations, you're able to start using faster for your CUDA development. And then everything else left is just for you to start coding things up. And whatever you're doing following this procedure should be sufficient for you to just compile and run it and submit any job. It could be very complicated, but as long as you can get your CUDA code uploaded and you can direct edit it on the using VI, which could be hard, or you can edit with your favorite IDE on your laptop or workstation, and then you can upload your code to the server, and then you can compile it on faster and run it. So that's basic workflow. Even for me, I'm working that way. I usually do the local development on my laptop, and then whenever I think my code is ready to be executed on faster or some other GPU nodes, I'll copy my code over and compile it and run it over there. So the basic workflow is it's just like this. Even for advanced developers, they have to do this. Remote editing is not always fun. Sometimes you get network problems, and all the changes you modify will get lost. So, okay, see, we spent about half of our short course just getting you all started. We haven't really touched anything about CUDA yet. But starting from the next slide, we'll be getting into the basics of CUDA. So, what is CUDA? CUDA back then it has an abbreviation of a computer unified device architecture. And if you look at the abbreviations, it's CUDA, right? It's CUDA. But now CUDA is just CUDA. And no one go back to ask you what's the meaning for CUDA. In some way similar to Texas A&M, we have A&M. No one going back to ask what A&M is. We call A&M as a brand. The similar idea. So the CUDA has this design. It's trying to expose all the potential parallelism for GPU computing units, so that they can be mapped to different kind of applications. Either it could be task-based parallelism or data-based parallelism. So data parallelism in a sense that all the processes are dealing with different data sets, but you have the same processes. And now with the latest version of CUDA 12 and some other pre-version also supporting dynamic parallelism. So you are able to launch your kernels on your device, and you can do a lot of fancy things that you cannot be easily done before. So today we are not going to the details about all those advanced features, but that makes it possible for you to think about how to use the latest features to map to your problem. Even some problem you might not be, when you're familiar with those problems, those might not be easily portable to CUDA, because the way how the structure of the code gets generated, dynamically. If you have a big chunk of code dealing with a big array, but suddenly you want to create another big array to do a lot of computation. And think about this: if you are using some older version of CUDA, you have to deal with all these things on the CPU first, and then you go back to the GPU to move the data to GPU and do some calculation. And use some latest features of CUDA, the dynamic program parallelism. You can launch your kernel on the GPU and launch another kernel inside the GPU to do all the calculations. And this makes it possible to port a lot of more interesting applications on GPU. And of course, you'll get a lot of performance gain by doing that. And also, that's the beauty about all this architecture, and it keep evolving, and it's all the new features, and it could be leveraging all the computing capabilities that hardware can support. And this architecture also has this beauty of this retaining performance, which is quite amazing. A lot of slides I'm presenting today were used by me and many others several years ago, 5-6 years ago. The basics of CUDA hasn't been changed a bit. It's kind of like a C now to me. All the basic usage of CUDA is not changing. So any code you read, as long as you're not using some fancy libraries, which might be phased out because of some other things. If you're just writing code writing some CUDA code from scratch, not using external libraries, your CUDA code should be still compiled and be executable on current architecture. And in most cases, your CUDA code can benefit from the upgrading of the hardware, just like a C code, a Fortran code back then for CPUs. There are some variations. For example, firming, from firming to what's the next one? I forgot. There's one particular version of firming card has a many floating point operating units, can do a lot of floating point operations compared to the next generation. That's the only time I noticed some performance drop when you're upgrading your hardware, because if you don't do any careful reprogramming of your CUDA code. But other than that, every time you upgrade to a new hardware, new NVIDIA GPU, your performance is either directly proportional to the hardware, the number of hardware or performance hardware they claim, or it's just directly you can directly benefit from the increase of the frequency of all the cores. And that's something pretty amazing for architect like CUDA, which it's not an ISO standard, right? If you're talking about C and C++, those are ISO standard. Those should be supported by I'm not sure, hundreds, probably many vendors that can supporting those standards. So CUDA itself is based on industry standard, but itself it's not standard. It's NVIDIA's product. So that's something you should be keep in your mind. And also, there are some small set of extensions could be enable heterogeneous programming. You can use the CUDA together with MPI and different programming models to make your code really scalable to extremely large systems. And that's actually a pretty common practice nowadays. If you write a code to targeting heterogeneous systems supporting many GPUs, and that's the state of art of the parallel programming and distributed computing for many applications. And also, CUDA provide a lot of APIs that you can directly use them to manage devices and memory, etc. So it's not just a program language; it's coming with extra runtime libraries and extra runtime libraries for you to leverage the resources you have, and also some external libraries like math libraries and also deep learning libraries for you to do a lot of other things. So it started, I believe the very first version of CUDA is started a bit earlier than 2007, but then the first release, the first generation of Tesla GPU together with CUDA in 2007. That's when a lot of things happened. 2007 is a magic year, right? I believe iPhone was released that year. It's about that time. And before that, a lot of programmers like me, and I was not using OpenGL, but I know a lot of researchers that they are starting using OpenGL to do some computation, mainly because they started noticing the computing power that GPUs had back then. they're writing C code or some other code, but they're using OpenGL libraries to mimic the way how the graphical programming is about, by mapping all the texture, shader, all those kind of all those structures into data arrays for fluid dynamic simulations, for particle simulations. So by using that feature, they can use OpenGL libraries to help them do the numerical calculations. And that has been a pretty hacking way of doing all the computation stuff and computational stuff, and that has been there for several years before CUDA was released in 2007. And then the current stable version is a 12, and gradually CUDA has been evolving, supporting new hardware features, and by itself, it's trying to improve its internal algorithms and also developing new libraries. So it's a pretty long history of development, starting from 2007 to now. It's about 16 years already, right? So talking about CUDA, there are two basic concepts you need to keep in your mind. There's always a concept about host and device. Since CUDA is not hosting any operating systems, it's not able to managing all the devices connecting directly to your CPUs. So itself, it's considered to be a device on top of the host. But this is the terminology used in CUDA programming architecture. If you are familiar with OpenSEC, CPUs, GPUs, FPGAs, IPUs, whatever you bring the context OpenSEC, it's a device. So everything is equal. So OpenSEC is more democratic in a sense, everything. But here in a CUDA design, it does divide your host and the device into different categories that treat them differently. So that's something you want to keep in mind. So whenever you have a GPU CUDA programming, you need to think about the difference between host and device, and the data communication back and forth. That's also something very important to keep in mind. So this is a very simple, I'm not saying simple, but it's a straightforward demonstration about how this heterogeneous computing is working. So we start with some serial code. We have a code here. Just we don't need to pay attention to the details about this code. Just we know that there are some part of the code cannot be parallelized. It's called a serial code. There are some functions that we know it could be parallelized. It's a parallel function. We can use it called the parallel function. There is some parallel code can launch the parallel function to help you to do things in parallel. And then you have other serial code. So it's in general, in most of the code we'll be dealing with in real life, it will be a mixture of part of the code that could be parallelized and part of the code cannot be parallelized. So it's like a sequence of code sections, and you do things separately. So for most of the serial code, almost all the serial code are usually handled by CPUs. And of course, if you copy everything to the GPU, you can use one single core on your GPU to handle the serial code, but that might not be beneficial. So that's usually why it's still pretty common to use a CPU to handle the serial code, and then you offload your parallel processing. If you have, the same function, if you want to calculate, say, the color value of a single of the pixel, you can, if you have 1 million pixels, right? You just send it to all the cores on the GPU for the GPU to do the calculation for you. They can do this all with one calculation, and as long as you have enough core to do the calculation all at once, you can, with just one cycle, you get all the values calculated. So that's the power of this parallel programming that you can do on GPU with all the CUDA cores. And then again, after you get some calculations, you need to get the data back, because GPUs cannot directly control your main process. You need to return the control back to your CPU. And in most cases, you need to summarize the results back or send all the data you can back to the GPU or CPU, I'm sorry. So that's the time spent to do the data transfer. That's time considered to be overhead. Data transferring in between CPU and GPU, that's always considered overhead. You want to minimize this time of data transfer as much as you can. And that's one of the main considerations when you try to do the CUDA programming, is trying to minimize the data transfer and maximize the saturation of the GPU. As long as you can consider if your computing time could be greatly reduced if you can divide your task into smaller chunks and use all the cores available on GPU to do all the calculations all at once. So that's the ideal case. In that case, you maximize the computing power by saturating all the computing capabilities of the GPU and fully leverage the computing resources available on GPU there. So this is another way to look at it. So consider this is like a simple processing flow. So we have a CPU to the left here. It has a bridge between CPU and a CPU memory. That's main memory on your computer. If you have 32 gigabytes of memory on a computer, that's a memory your CPU can have access to. But the CPU cannot directly write to the GPU memory because that's under control by GPU. You don't want to touch that territory. CPU have full control of the memory here. So to get started to run any GPU code, you first copy all your data from your CPU memory to your GPU memory. It's reasonable because GPU, all the CUDA cores, I'm talking about simple scenario, but currently there's a so-called GPU direct technology. With hardware support, you can directly have access to the main memory from GPU cores, but that's not something we're talking about. We are talking about, this simple scenario without any extra hardware support to enable GPU direct. But this is a very generic case, and it's still commonly used. So to do this with the GPU to access to the CPU memory, the data on CPU memory, you need to copy the data from CPU memory to GPU memory. That's required for a regular CUDA programmer, and that's something you need to do. That's an essential step. And then you need to load the GPU program and start run it. So GPU program, usually it's a very simple program. You just need to do a very simple task. It's so simple, you can load this on every CUDA core and run them. Just consider if you have very complicated function and very complicated instructions, if they cannot be easily loaded on the CUDA cores, and if the CUDA cores needed to take turns to execute part of the GPU program, then your efficiency might be greatly reduced. So the whole idea of this maximizing the performance on GPU is to make this the computation on each CUDA core as simple as possible, but you distribute this computation as many cores as possible. So you can leverage each computing power of each core to maximize your performance or through output. So you minimize the total time taken to process all the tasks you send to the GPU. So then after you load your program, that's a kernel. Some of you probably still remember I talked about launching kernel. This is more or less like launch the kernel on the GPU, and the GPU will take the data you copied from the CPU memory to the GPU memory and start processing. After you get everything processed, the data will be saved back to the GPU memory, but the CPU cannot see it because it's GPU's memory. You don't have access to it unless you have a synchronization step. You copy all the data back from GPU to CPU, and then your CPU program can see the data and you can do something about it. And you can move forward to your serial code, or you can jump to another parallel code, launch another kernel and repeat the pattern. And of course, if there's no serial part between two parallel parts, there's no reason why I needed to copy data back and forth. You can keep your data stay in the GPU memory and continue processing your data. That's the way how you maximize your usage for GPUs. You don't want to copy data back and forth unless it's really necessary. Okay, so we have been talking about data copying back and forth, but starting from CUDA 6.0 in 2014, NVIDIA starts supporting unified memory. It's a software support. There's no hardware mechanism built in to support unified memory. And in the sense that you can just define one memory block that could be viewed, could be directly managed by CUDA runtime. So when you want to have access to a particular variable, you don't need to worry about if it's in the GPU or CPU. So whenever the data is accessed by either CPU or GPU, the CUDA runtime will notice that, hey, this data actually is still in CPU. I'll do this copying back for you. So that's what the runtime is doing. So it's mimicking the way of data copying should be done, and it's all done automatically based on the request. That whenever you need access to the data, if the data is not on your memory, the CUDA runtime will do it for you. So to a programmer, it's transparent. You don't need to know if it's a GPU or CPU, the data, as long as you define it as a unified memory block. So there is a special structure that you need to define allocate your memory. If you do it in the traditional way, just like a malloc, CUDA doesn't care. It's just CUDA will treat them separately. But if you define a unified memory malloc, so CUDA will treat them as a unified memory. So it's like an extra feature. It's not something completely replacing the previous way of doing things. So we can still do all the things manually, but this unified memory mechanism provides this way for you to unify this memory transferring. Now you might ask, why? Why do people just throw away the traditional way of doing that? Just everyone can use unified memory. The problem is it's not so efficient. For some problems, if the programmer knows or understands exactly what data they need, they can do this in a very efficient way. They can also try to do this in synchronous. They can do it synchronous to the computation. So while you're doing the computation, you can assign one GPU block to copy data back and forth whenever it's needed, because you know when the data will be needed and when the data won't be needed. So you can do this asynchronously while you're doing the computation. And you can maximize the data transfer and also maximize the computing needed, which is actually more efficient to do it that way. So that's why unified memory is not widely used, mainly because programmers are very confident about their programmability, right? So we don't trust the machine to do this for us, and we will continue doing that ourselves. But since a little bit different, starting in 2016, in the Pascal, it's a P100, P starting with letter P version of GPUs. Can you comment on minimizing memory extent between device and host with keeping good code structure? So we'll talk a little bit about that in the coding part. So I'll get back to this question, but I think it's a very good question to ask, especially when we talk about unified memory. So starting in 2016, we have the newer version of the Pascal GPU, not we, NVIDIA has that. So it provides some hardware support for data transfer. So that has a very special pager lock. So whenever there's something needed, the hardware will do this asynchronous for you. And by doing that, you can greatly reduce the burden on the programmer side. Say your programmer doesn't need to worry too much about when and the data should be copied, and there's no need for a programmer to worry about pre-fetching. Before the data used, sometimes the hardware knows that may predict that the data might be used by the particular device, GPU or CPU. It will help to synchronize the data for you based on some hardware pre-fetching mechanism. So that's the hardware support, making it much more efficient than just doing all the things yourself manually. And at least on the programming side, you don't need to write a tons of code to worry about when you want to do the computation, when you want to do the data transfer. And that actually changes the way how the program is written, for some programmers. They started using unified memory a lot after 2016. So I already mentioned about this particular malloc. So it's especially called, instead of CUDA malloc, we'll get into this, but I just want to show you all that the major difference here is there's an extra keyword called managed. So standard way of doing memory allocation on GPUs is called a CUDA malloc. But now with some CUDA malloc managed, it will manage the unified memory for you. So then you can greatly reduce the extra code needed for you to do the data transfer, etc. But you need to use one extra function, it's called synchronization, which is needed whenever you want to do the synchronization before the system before the system knows exactly when to do the synchronization, you can use the CUDA device synchronize to make sure the CPU and GPU memory are synchronized. This is important whenever you do some changes in the data, and then if you want to make sure the next step in your code will get all the data synchronized between CPU and GPUs, and then you want to use this CUDA device synchronize to make sure the data got synchronized. Okay, in the example I showed you this hello world, and this is a standard hello world for C and C++ developers. And what a NVIDIA compiler does, it takes this code and directly call the host compiler, because it's a standard C code. So there's no reason why NVIDIA needed to create a brand new C code for this. So you can call the host compiler, either GCC or Intel compiler can directly compile this code for them, so it can call this directly whenever needed. So that's why NVIDIA will treat the host code and the device code separately. They are also using the different compilers to deal with different part of the code. So NVIDIA compiler is just could be directly used to compile C code, and because it's already compiling the device code, and it does have the capability to do the traditional C code compilation. So this is the device code I showed you all. It's just a dummy function, my kernel, nothing more, nothing less. But you notice there's two extra things here, two new syntactic elements. Okay, syntactic elements are the things you want to pay particular attention to, because that's the part which make this CUDA code different from C code. One of them is underscore, global underscore. Okay, so that's one. The other one is a triple brackets here. We have my kernel less symbol, one greater symbol. Okay, brackets. You use them to launch kernels. So you define a kernel, you launch the kernel. But what does 1.1 mean? We'll talk about that later, because that's very important for CUDA. That's I believe is one of the most important things you want to learn about CUDA is the meaning of these two numbers, 1 and 1 here. Okay. Now think about this way. If you want to write a CUDA code, all you need to worry about is first to write a function to deal with the calculation for individual task or individual data block. That's your CUDA code. That's my kernel. That's my kernel. There's another part in your CUDA code that you want to pay particular attention to, is to how to launch this one. And the numbers you put into this launching kernel launcher defines which particular core you want to launch it, how many threads you want to use to launch it, and how many blocks you want to launch it. And we'll go into all the terms, in the next several slides. You'll see what I'm talking about. But see, my kernel launcher, this kernel launcher maps directly to the hardware design for the CUDA code. That's exactly the reason why CUDA is so powerful, because you have fine control of picking a particular CUDA call, not in the pool of CUDA code, because you don't go directly to the particular CUDA code to run it. It's just in this virtual pool of CUDA cores, you can pick how to arrange my kernel to run on those cores. So CUDA is providing this interface for you to do this fine control. Think about C code. You don't have this fine control about which kernel will be launched to which core, and OpenMP can help you do that. But for the regular user, if you are just using your compiler, you don't have this control unless you are using OpenMP or OpenSEC to compile your code to run it on CPU. But then you are more or less adding extra comments to your code to help the compiler to understand which part could be parallelized. How can I cut your loop into different small pieces and can launch it in different cores? But this syntax that CUDA is using, to me, it's more elegant in the sense that it maps well to the structure and give you more freedom to adjust your choice of your, the number of threads and number of blocks, etc. So we'll get into the details. So as I mentioned, there are two things. One is this one, underscore, global underscore, which means this is a function that runs on the device and it's called on the host. See, it's here again, even for this definition, it has a very clear boundary between the device and the host. So the global function defined in this way is only callable from the host, and it runs on device. If you don't have this, if you just have a void, my kernel void, that will be a host function, just like a regular function. It will be called from the host and it runs on the host. But this global more or less like tells CUDA compiler and runtime say, hey, this is a function. You can call me on CPU, but I can only run on GPU. So that's basically the meaning. It's more or less like a pragma. You are telling the compiler, this is kind of special function. Just treat me specially, right? And the NVCC also separates source code into host and device components. Host code will be functions. If you define this as a device code, it will compile this my kernel with device compiler to compile into different binary code that could be run on GPUs as a PTX code. You can learn more about those code on some other resources. And then there's a host code. You can directly process the standard using host compilers, ICC, Intel compilers, or GCC. You can compile this main function. But there is the tricky part, the special kernel launcher. It will be handled separately. So that kernel launcher will be specially handled by the NVIDIA compiler. It will translate into a function called inside this host code. The host code will call the kernel function with extra information you provide with 1, 1 or 1, 2, all those numbers, 2 numbers, and then you can launch your kernel in a certain way. And how to launch it, that's something we'll talk about. So this triple angle brackets, that's brackets mark, it's a call from the host code to the device code. So that's how the host code knows that so NVIDIA has its own front end. Actually, when it's compiling the C code, it does use built-in GCC or ICC, depending on which host code you are specifying. When you build your CUDA, install your CUDA installer. If you do anything from scratch, it will ask you to specify which compiler you want to use. So it will be using the compiler you specify when you install CUDA to compile the host code for you. So you can choose to use a PGCC, the Portland group that bought by NVIDIA. You can use ICC or you can use the GCC. So this tells you that how to launch a code from host, and it's also called a kernel launch or kernel call, function call. That's parameter. I'll getting back to that in a second because that's something very, very important for us to understand how the CUDA is working. So this one, when you run it, what you have is just a hello world. So the kernel doesn't do anything. It's a dummy function, as I mentioned. And you get to return 0, and then you print out. Actually, the print function itself is a main function. It's a host function. So even print hello world, I'm not printing out from my kernel, from my GPU. I'm printing from a CPU. It's nothing different from the host code I just showed you previously. It's the only difference. I have launched a dummy function, and that's it. So that's kind of like a trivial question, and let's go back to look into something more interesting. We want to leverage the computing power for the GPUs, and if we just do a number A plus number B, you get C, and this cannot be parallelized. 1 plus 2 equals to 3, right? You can do this with a single GPU CUDA core, and that's it. There's no way you can parallelize this kind of problem. It's whatever you do will definitely make your code slower, because you can directly use a CUDA core to do the 1 plus 2 equals 3. Now the beauty is, if you have vector A and vector B, which A could be 1 million elements, B could have 1 million elements. Of course, you should have a matching. Otherwise, there's no way you can do this summation, right? It doesn't meet the requirements for the mathematical operation for vector addition. And then you try to calculate C. You can do this 1 million addition operations. If you are running a CUDA core, CUDA cores can launch this, of course, you cannot fit in 1 million directly, but you can do this in sequential. You can have first set 200,000 to the CUDA core and get a submit. You can do the rest. So there are special CUDA to handle that number of elements, and if it's too big, it's more than the CUDA cores you can handle. But again, this will help make it possible for you to do all the calculation all at once. Just consider, let's consider small. 1 million might be too big for you to fit into once. Let's say 1,000, which is pretty small, compared to the CUDA cores available on your GPU. Not a CUDA core, I'm sorry. The threads you can use to do the calculation. These are virtual threads. I'm not going to talking about physical one, because physical numbers for different versions of GPUs, they have different number of cores, but the virtual threads, they are more relevant to programmers. You don't worry too much about how many cores you have, because CUDA handles those mapping between the virtual threads and the cores internally. So for most programmers, you're just worried about how many threads you can handle, and the rest, it's problem of CUDA runtime to decide if the 1,000 thread could be fit into, say, several hundred stream multiprocessors. How do they do that? That's CUDA's problem. But for us, we just need to worry about what's the maximum thread that CUDA can allow me to run for the single operation. So we'll get back to the details a bit later. Okay, so very simple case. If we have 2 integers, right, A and B, and we can define this global function and it will take the integer A and integer B and get the results written back to integer C. So for those of you who are familiar with C and C++, we're using pointers, we're using the address. So C, B, A, these are pointers. It's just a memory address. And the star here means I want to get the value from this particular memory address. So what you're doing here, you're getting the value from A and B and add them up, and then save to the memory where C is located. So that's what this function is trying to do. So as before, this underscore global tells us that it's a CUDA, it's a CUDA C and C+ keyword, meaning that this addition will be running on the device and it'll be called from the host, okay? And then there's one issue here. When we talk about memory, when I talked about memory previously, I'm talking about memory in the GPU, because why? Because this global function can only be executed on the device. When I say the pointer pointing to the memory address, this memory address should be the memory address in the GPU memory, not the main memory. But how can we get access to the GPU memory? That gets back to the very next thing you have to do in CUDA, managing the memory on GPUs. Of course, you can use a unified memory management. We can talk about that later. But before we get into that topic, you need to learn how to manage the memory GPUs. It's a very important thing. Actually, help, even though in the future you want to use a unified memory management, but it's helpful for you to understand many things that are ongoing with CUDA and the performance tuning, other things. So learn to understand the basic memory management is very important. So there are 3 basic CUDA APIs can handle memory management on device. If you're familiar with C, it's just identical, or it's just directly one-to-one map from the CPU memory management. You have malloc, memory allocation. You have free your memory allocated for dynamic memory management on CPU devices or CPU memory. Then you have a memcopy. Of course, if you are familiar with the standard library, there's a relocation. I'm sorry. There is another. You can allocate. Again, reallocate. There are some other auxiliary functions inside the standard library. If you're familiar with the C, can do something more. But these are 3 very basic memory management APIs. It's also standard way of doing that in C and C++. Or C++ usually use new and delete, but it's probably that's C. It's a C. Malloc and free and memcopy. It's pretty commonly used. Now, let's getting back to our AND kernel. So we have this function, and we want to allocate memory on GPU to do that. So let's look at the main function. For the main function, this is what we are doing here. We have ABC, integer ABC. This defines 3 variables, ABC, in the main memory. Actually, ABC, when you compile this, will be mostly using registers to store the information ABC, but we don't worry too much about where the storing in the memory because that's not our concern. We define 3 extra pointers, DA, DB, DC. These are referring to device A on device memory for A, device memory for B, device memory for C. So we use 3 to refer to the memory we will be allocating on the device. And for those of you who are not familiar with the size, this is a standard way of doing that, so that this size could be referred to different data types. If the integer is just 1 byte, depending on integer, it's 8. Yeah, I believe it's 1 byte, right? Someone can correct me. I said long will be 16 byte or 32. Integer is 16 byte. Just forgive me. I mean, if it's a counter, it's just simply just 1 byte, right? Integer will be, I believe it's 8 byte. If I have a long, probably 16 byte. If I float, it's 32. Float is 32. Double precision is 64 bytes. So the size here, using the size of function, make it easier for you to handle different data type. So that's pretty common use technique. So just consider this something you want to use yourself. It's not, you don't have to do this. You can directly use the numbers there, specify the size, but it's recommended practice for you to handle some generic data types. If you define a class or define a structure in C, this structure might be pretty big, containing multiple integers, multiple counters, multiple strings, and then with that size of, you don't need to do the calculation, it automatically give you the size of the particular type. Okay, integer is 4 bytes. Thank you, Zhenhua. So long integer is 8 bytes, so that's good. Let me go back to. Okay, where is it? This is, okay. So now you allocate the memory on the device. You get 3 pointers, DA, DB, DC, with the size defined by integers, because that's the size you want to keep the same so that you have consistent memory size to store the variable. And then you can set up your input value, A and B. So the next step, as you remember, you need to copy the data from your main memory to the GPU memory. So this CUDA mem copy will copy your data from A to DA, the very first one. And also there is also a direction flag. It's just like it's a flag. It's just telling you that this will be copying from host to device, so that you can have the same function. Otherwise, you can define 2 different functions. You can define CUDA mem copy device to CPU host to device, or CUDA mem copy device to host. And then another way is to keep the function name the same, but have an extra flag that you can use to indicate the direction. So that's what CUDA is implementing. Actually, again, you can have 2 different functions, but this is probably the way the CUDA, architects, they think is probably a better way to do it. So now what you're doing, your first sentence is copying statement. It's copying data from the host to the device. The second one is the same, but it's a B from the DB. So, and then after you copy data to the device, to the GPU, you can then launch it. So remember, we have this AND function. This AND function is already defined, and it's just trying to get A plus B equals to C. And you are launching this on 1 thread. 1 here refers to 1 block, 1 thread. Actually, it's just 1 thread. We'll get back to this a bit later. We'll talk a bit more about that. After you get the results calculated, so this function, after it's launched, the device C memory address will be updated based on the value you have from DA and DB, and then you copy all the thing, the results, back to the host. And now pay attention to the last flag here. It's CUDA memory copy device to host. That's a direction flag. It's basically copying the data back to the host. And then after everything is done, you free your memory CUDA free will be freeing the memory, on the CPU. I'm sorry, on the GPU, because you didn't allocate any memory on CPU. You are directly using A, B, C as an integer. You don't need to free that. But when you are dealing with arrays, as I'll be showing you in the next example, you need to do not only freeing the CUDA memory, but also need GPU memory, but also need to free the CPU memory. So next we're going to parallel. So things are getting more interesting. We just did a very simple one integer addition, which is kind of boring because you're not using any extra features that CUDA is programming to make your code running faster. Actually, your code should be smaller, much slower than your CPU, because you need to copy data back to and from this GPU. And your CUDA core is usually at a much lower frequency than your CPU core. So you are expecting to slow down your calculation by doing this CUDA programming, which is definitely not what we want. So how can we overcome all this overhead to have a faster and more efficient code that can run on GPU? The solution is to saturate your GPU by giving your GPU more work to do, so that the time taken to copy data back and forth could be smaller compared to the total time taken to do the calculation on the CPU. So by doing that, you can greatly leverage all the computing power that on the available on GPUs, and then the overhead that you are introducing will be negligible, so that you can achieve speed up. So that's a whole philosophy behind this GPU programming. Basically, you want to fully leverage the computing power there by saturating the computing resources on GPUs, so that you can overcome the overhead introduced. That overhead is inevitable. You have to deal with that. There's no magic that you'll skip that unless at some point NVIDIA decide to design an operating system that can run on GPU. That will be a different story. But as far as we are dealing today, we have to worry about overhead for the data transfer. Okay, so here, what we are going to do, we are modifying this code, just changing this AND 1 to AND N1. What it does is actually doing all this calculation on N threads. So you are doing all the same calculation N times. If you are just doing very simple A plus B equals to C, you're not getting much, even though you are using all the cores to do the calculation, but the final result is just single number. You're not getting any performance. It's just, just testing things. You can test things out that way. You can run, you do run on multiple cores, but the result is just a single number. It doesn't give you extra benefit. The benefit only comes when you start doing vector addition. When you try to define not just two variables, you define two vectors. So the global function will be modified a little bit. So global function here, if you can look at here, we'll be using a predefined constant keyword block. This block is a CUDA terminology. It's something predefined in CUDA. So block idx.x, that's a predefined constant in CUDA runtime. It's not a variable. It's a constant. For a given architecture, for a given GPU, block idx.x and block idx.y and block idx.z, these are constant. Kind of like a macro you can define. If you're familiar with C and C++, macro, you can define some constant like pi equals 3.1415, whatever. Then you can continue using the variable. The variable will be replaced by the constant before you compile your code. That's called a pre-processing, right? So here, block index.x, that's a constant. Even though to us it looks like a variable, but it's constant. Okay, that's very important to keep in your mind. That's the same for all the for all the CUDA programs. So by using this block index.x to index into the array, so each block can handle a different element of the array. So that's the tricky part. And that's a part that if you figure it out, probably you see how the CUDA program is working. Let's go to the next one. So there will be another grid, a keyword on the grid. We'll talk about that a bit later. Okay, so consider we want to we have this function, which is defined as a global function. This global function will be running on the device and callable on CPU because it's a global. Remember, that's very important. Of course, you can replace global with a device. So the device will be callable on device and executable on device. Or you can define underscore host. That will be callable on a host and executable, runnable on a host. So global kind of different. It's just like callable on a host, executable or runnable on the device. Now, if you define this function and A, B, C here, these are 3 GPU memory blocks. That will be each A here is referring to the first address of a block of of the array. B is the very first address of the array. C is the same. So A, B, C here, these are 3 vectors. So by using this particular notation, C blocks index X and A, etc., plus B, etc., you are adding each element. Okay, given a thread, this block.x is given. So, for example, if you're here, I'm talking about, I'm mixing up the thread and block. Let's forget about the thread itself. Let's call it block. So instead of using thread, we use a block as an indicator of which one you're running your code on. Okay, which thread you're running your code on. We call it block 0. Actually, that's considered it's a thread, but we can't call it a block. We'll go back to correct the idea a bit later. So if there is a one particular CUDA core, I'm sorry, it's handling the block 0. So this CUDA core, when it's trying to launch this global function, the block ID index.x will be replaced by 0 because my particular CUDA core is labeled with this block 0. Okay. Then this particular core will be handling C0 equals A0 plus B0. So I'll be handling just one element or your array addition. That is fine. That's my job. I handle my particular case. I'll finish my job and I'll return my C0 to you. That's my CUDA core's job. And that's it. Now, his neighbor or her neighbor, the block 1, will have a different block index X, which will be 1. So what this CUDA core handles will be handling C1 equals to A1 plus B1. The same goes for all the other different CUDA cores. Each CUDA core will have a unique block I index.x value pre-assigned to it by the CUDA runtime. And that one could be used by, this index could be used for the CUDA programmer to do the element-wise addition and other operations without knowing if this particular one is running on particular CUDA core, because the CUDA runtime will help you to do the allocation, to distribute your computation to different CUDA cores. And currently we're using block 0, 1, 2, 3 to label those. And each CUDA core will be taking the index and directly refer to the element for your array and for you to handle this computation. So let's go back to the parallelized kernel. That's the one we have been reading. So the kernel here will be not just C equals to, star C equals to. Yeah, that's a good one. It's, that's memory leak is a big problem for C programmers. I have been dealing with that for the whole summer as an intern working at a center. It's horrible. I spent like whole summer just figure out all the bugs for some memory leak dealing with strings, and that's good. So now this program takes all the indices. Those are predefined indices, and CUDA runtime handles all this for you, which is pretty neat. So you don't need to worry about the details. Let's look at this particular example. It's a bit more complicated, but just follow me. You'll probably get it this one. So we start with 3, the same way. The only difference is that we define a very big number. It's not that big, 500, but it's not small. So we define, instead of just one variable, we define an array, and we need to allocate this memory block for these 3 arrays here, and DA, DB, DC. If you are not familiar with the malloc, this is exactly the same syntax for malloc, but you needed to understand that you're now needed to have have a second, there's a pointer to the pointer to refer to the memory that for all the different devices. That's how malloc is working. So you need to convert them to a void pointer to pointer. Otherwise, this will give you some error message. So let's see, A, B, C. These are three vectors on the host. So you can use a standard malloc to analyze it, to allocate the memory. Now you can easily see the difference between CUDA malloc and malloc. Malloc is a standard C library, and you can use to allocate memory. But CUDA malloc is using different syntax, a little bit different. They are doing exactly the same thing. It's trying to allocate memory for arrays, but one is on host and another one is on device. So the random init here, this is just two functions. It's not, these are not a standard function. You need to write these two functions yourself. What it does is very simple. Just randomize to randomly initialize your A and B, so that you can get a initial value to work with. Okay. So the next thing, as you all probably already understand or now to remember, we need to do the data copy. So after we randomly initialize A and B, and we need to copy all the data to the device. So exactly the same code, nothing changed here. And then we launch this with and N1. So what it does, it will launch this and kernel function to N blocks. Okay, forgive me about this terminology, blocks. We'll talk about blocks and kernels. It's just like X and Y. Blocks here, you consider it like a Y, X is like a 1 here. We'll talk about that a bit later. So consider we want to allocate this to N blocks. So that means I want to use my N CUDA core or CUDA threads, N CUDA threads, even though it's N blocks, but actually you're using N CUDA threads because the total number of threads is N times 1. If it's N2, it will be N times 2. You want to run 2 threads per block. Now it's N block. So what this one does is you want to run 1 thread per block with N blocks. Okay, and I'll get back to that. Why we want to do that? It's kind of, it's non-trivial question actually. Why we don't use and 1N instead of N1? I'll get back to that a bit later. So assuming this one is calling this and kernel and do the addition, and then you do the mem copy and you get the data back, and then you free your ABC, just like what I mentioned on the host, use the free function. You need to free both the host memory, dynamic and allocated memory. Otherwise, it will be, be memory leak here and there. It's kind of messy. And then you need to free your CUDA memory. So this is the whole, pipeline. Even though you're writing a CUDA code to solve Navier-Stokes equations, you are more or less doing something like this. The basic workflow is the same. The only difference is that the launch function, the kernel will be different, right? Or you might have multiple sections code like this, but the basic workflow, it's the same. Initialize your data, copy to the memory, GPU memory, device memory. You launch the kernel, copy it back, clean up. Or if you have a time evolution code, if you solve some partial different equations to evolve, say, to solve, say, heat dissipation equation, and you do this for every time step, right? If you want to output, it's fine. Let's copy the data back, output it. Let's go back to loop again. Let's use the previous time step, because you don't copy data back. Oh, I'm sorry, you don't copy data back to the GPU because you can keep the data in the GPU, continue using that to evolve to the next time step, and continue doing this, iteration after iteration, continue evolving. That's how you do the time-based evolution, right, on GPUs. So you don't need to copy data all the way back to the GPU, because GPU keeps the current status of the temperature, pressure, etc., all the information. And you can keep doing that, but you need to copy data back whenever you want to output. Otherwise, you cannot easily get the output. You can probably want to do some post-analysis. You want to calculate how much energy this current system is. Then you need to do some analysis, or you can do the calculation directly on the GPU and then analyze the data back to your CPU for outputting and other things. Whenever you want to deal with I/O and other things, you probably want to write it back to CPU. But again, I want to mention that with the GPU direct, you can directly write to I/O from the GPU. And that requires some special support for the networking devices. There are some particular version of drivers needed to be installed. But most of the latest GPUs that support GPU Direct. And that's some feature you probably want to explore in the future. But for this course, for this short course, we are just considering this a standard workflow that you want to follow, at least get you started with some standard, CUDA programming procedure. Okay, so for unified memory, and this is just one example showing you how you can do the unified memory directly. What you do here, you do the CUDA malloc managed allocate memory with a return value here. You do the same addition, but you notice that we don't copy data back and forth anymore. We will save two statements, copying data to the GPU, copy data back from GPU. But we needed to call the CUDA device synchronize to make sure the data got synchronized between CPU and GPU before you really want to use the data to do anything. If you don't care, it's fine. You don't need to call this CUDA device synchronize because if you don't need to read the data, all the calculation will be done on the device. It's fine. But whenever you want to get the data processed and you want to use the data on a different device that calculated, different from the device or host calculating the stuff, you need to call this CUDA device synchronize to make sure the latest changes will be synchronized across GPU and GPU and CPU memories. So that's the one of the major benefits. You saved the two statements, but you need to add one more statement here, CUDA device synchronize. So it's always, it's a game, right? You don't need to worry about the synchronization unless you're dealing with very complicated scenarios. So for real code here, N is actually the size of your array, the problem size that you're dealing with. If you have dealing with 1,000 times 1,000 times 1,000, right? That's 1 billion. That's your N. But of course, when you want to launch this kernel, you want to divide this, make sure that you cut this into multiple kernels, you can launch them. We are not covered about how to do the very simple calculations that in this short course, but this is a straightforward way to do that. There's a very simple function. You can, you don't have enough threads, but I'll go back to, let me go back to the, because this is also relevant to another question previously, someone mentioned about here. So this is all the specs for the A100 GPU node. So there is one thing you want to pay particular attention to is the number of threads per block, which is 1024. So that's why when you try to launch a kernel with the N, for example, 1N, and if we launch a kernel with 1N as your parameters for kernel, so what you're trying to do is trying to launch N threads, but with one kernel or with one block. Okay. But the problem is because this limitation, this is a harder limitation. You cannot go over this. You cannot go over 1024 for one block. If you launch your add function, add kernel with 2000, it will be over this limit. You either get error or, if you are using latest version of CUDA, there might be some way to go around it. But back then, for some older version of CUDA, it'll give you error saying you're over the limit. You cannot go over, say, 1024 for the number of threads per block. So 1N is kind of always limited to you 1024. Now, if you look at N1, N1 here, N can go up to, 2 billion. So you can have 2 billion blocks with only one thread. So if you do the N1 here, N could be as big as 2 billion because that's a dimension of size of grid here. So this grid itself, it's virtualized, like a thread pool. It will help you to handle all the things, rearrange all your blocks, other things, make sure the kernel will be fit into your cores. All the total number of kernels will be divided into multiple groups. So NVIDIA CUDA runtime will handle this multiple kernel launching for you. So you don't need to worry about to fit into this all together, or how to do the math to fit in this one by one, doing the multiple kernel launching yourself. So this is a reason why we usually use N1 if you don't know how big the N is. So even if you have, say, 1 billion, 1,000 times 1,000 times 1,000, you can launch it directly using N1. And that's kind of, I don't know why they designed it this way. Probably some NVIDIA engineer can answer this question, but this is how they designed it. So that's the way how the CUDA working. So that's why when we try to launch the kernels, just be careful, about the limitation here. Okay, when the size exceeds 2 billion, do you need to? Yes. So if it's exceed 2 billion, then I don't know about the latest version of CUDA 12. It might be, probably 11 already. They're supporting automatically splitting the kernels for you, so they can automatically have just, kind of like when you're sending a text message with more than, I'm not sure there's a limit of 140 or 200 something. If you are sending a long article through text message using your phone, your service provider automatically cuts that into multiple messages or send it to you, or charge you multiple messages fees for them. The same idea here for CUDA runtime. I don't know how things are working this way, but it might be possible for it to cut this big multiple, more than 2 billion messages into 2 billion, not messages, 2 billion kernels, and then it will do all the multiple submitting for you. So, but if it's beyond 2 billion back then, for a couple versions back when I was working very, very actively on CUDA programming, we needed to deal with all this manual splitting ourselves. So it's actually very simple. You just do a division of this total number n divided by a certain number. So you know that it's go beyond a certain certain limit. You iterate. So you iterate submitting kernels one by one to fit into this limitation. But again, hopefully someone from NVIDIA can help me on this one. I needed to double check to, can follow up. You can follow up with me, email me later on. I can find out what's going on, because it's something I want to figure out myself as well for the latest version of the CUDA version that might be supporting launching a range much larger than what they can handle. They can probably automatically handle the indices and other things. Okay. We have a lot of things, but unified memory, and I didn't cover this thread, so okay, we covered this part. And unified memory, it's basically it's the very simple review about what we have been talking about so far. It's about the host and device, and make sure you understand the difference between these two, and also the global function. It's a global decorator, or whatever you call it. It's a specifier or decorator. You can use that to declare a function that is callable by the host and executable on the device. Given this global and also the kernel, you can start writing non-trivial CUDA programs already. And also be careful about memory allocation. And also every time when you're dealing with certain variables using the kernel function, make sure you know that variable, the memory of the variable should be allocated on the GPU as well, because the global kernel can only be executed on GPUs. You need to make sure everything is running, has a memory there on the GPU. So it's a kind of important. So non-chain kernels, you can use N1, which, as I mentioned, this N could be going up to 2 billion. And also there are multiple ways to rearrange this. And you can have a 3D blocks, 2D blocks. And as you can see, there's a block index X, as you may imagine, the block index Y and Z, and it gives you the dimension to rearrange all the structures. And also important to use NVProf to collect and view some profiling data, help you to see how many times this function got called and how long this function takes to finish, etc. Okay, thank you. I'm sorry, everyone sees your message. let me see. So this is another example using the without unified memory, and you can see some extra work you need to do: copy data to, copy data from, etc. And then this is a vector addition with a with a unified memory. This time I'm using a thread instead of block ID. I did this on purpose so you can see the difference. So the thread here, I'm using 1,000 threads, and I'm basically launching my kernel, vector addition kernel, to a GPU, requesting only one block, but 1,000 threads per block. And as you can see, the index here at the top here in the global function, it's not a block index.x. I'm using thread index.x. Those are like predefined keywords, like macros that NVIDIA runtime used to identify individual thread you are dealing with. With that, you can directly use this thread index to refer to your element. So every thread is dealing with individual element. So you can easily map each element addition to your processing core or processing thread. So if this one's the one you like Edwin just mentioned here, if you have 1,000, what it does is it will be launching 1,000 thread per block to 1,000 blocks. So this one will let's see, perform the 1,000. So it's actually performed this operation 1 million times, because for each block you have 1,000. It's like multiplication kind of relationship. But again, if you are depending on how you use this index. So if your blocks index X, you didn't use it, it will directly using the thread index X. It will be even for different blocks, the thread index will be repeating. For block one, it's a thread index going from 1 to all the way to 1,000. For block 2, the thread index is going all the way from 1 to 1,000. So if you're doing that, more or less like you're doing this 1,000 times, you're doing the same calculation 1,000 times, because if you're not using the block index to refer to the particular element in your array, you are just repeating the same calculation. Okay. So only when you have this many elements you want to handle, like 1 million elements, then you use a combination of block index ID times the number of block width. I don't think I have an example here, but I can show you some slides for the more advanced materials I prepared for different short courses. Then you can just like when you try to convert 2D indices into 1D. If someone give you a matrix with 3 by 3, right? Now I want you to give me the global index for the matrix if you counting all the way from the row wise, from first row, second row, third row. How can you give me the index, global index, 1D index? So you do it by multiplying the number of rows with the row width, right? The width of the row, how many elements you have in each row. And then you plus the thread, the column ID, the column index. In the same way, you can use a block index ID and blocks width, which is also predefined. Block width is also predefined. With that, you can put them together with the thread index ID to construct the one, probably very big thread ID to refer to your particular element. So you can do the same thing. Okay, you can use that to handle more complicated scenarios. Yes, so as I mentioned, if you know very clearly that what data need to be copied and back and forth, you don't want to use a unified memory for all your variables. You want to just specially pick some variables, say, hey, these are the variables that I want to use non-unified memory. I want to use a traditional memory allocation to deal with it because I know when I need to synchronize them back and copy them back and forth. And unified memory will probably introduce some extra burden because it's trying to do things as smart as it can. A lot of prefetching might be needed if you use a unified memory. So it will be predicting that you might be using this data on the device. Probably you don't, but it's trying to prefetch some data to the device before you start using it. That will introduce some overhead, even though it's probably very, very small with the hardware support. But it's again, it's something you can avoid if you really know exactly what data you need on the GPU or what data you need on CPU at every time step when you do the simulation, etc. And that's why in my code, I don't usually use unified memory, mainly because I know exactly what variables I needed to update at every time step. I do that manually, and then I need to do that manually across multiple GPUs and using MPI. And that's a lot of tweaking in the way how the data got synchronized. So in that case, it's better for me to manage the data myself instead of using unified memory. It might be messing up with whatever prefetching scheme that CUDA runtime is trying to support. So sometimes the runtime is trying to be smart, but again, I believe there might be some ways you can disable this kind of prefetching and directly using this runtime. So CUDA has been evolving and with all the different features supported, but they're always some way to disable them. It's probably better to look into the details, but that's probably the situation I can understand that in the situation that for sure that data transfer is needed or not needed, then you probably want to handle the data transfer yourself, which is usually more efficient. So these are some extra examples I'm showing here. And lastly, we still have some time, a couple of minutes. So we want you all to learn some basic about data, device management, because in many cases, you are not dealing with one device. You want to deal with multiple devices. With multiple devices, you probably want to either you need to spawn a thread to manage a different device, or you want to have an MPI process. Each MPI process, if I'm writing a distributed computing software, you probably need to get familiar with MPI anyway. It's very, very powerful. It's widely used. It's pretty mature, and it has been well tested. So the whole community, parallel high-performance computing community, is using MPI. Of course, there are many other different programming models, but MPI will be staying there, and it has been proved to be working well for many applications. So with MPI to control each process to control each device, that's probably the optimal way to go if you have multiple devices to play around. And the way to do it is to use a get. There is a not this. I'm sorry. Let's go back to this one. There is one CUDA device synchronized, and also the CUDA get device ID or set device ID. For each MPI process you activate, you can in your MPI process you can get the device ID, so that you can set the device ID to be matching with your MPI rack index. That's something I didn't show it here, but when you're doing MPI program, you should know there is a rack here for each MPI process. That rack indicating which MPI process you are inside your inside your communicator. That's what MPI, more or less like an environment for MPI programming. It's called a communicator. Inside your communicator, you can have multiple groups, or you can have only one group, and everyone has an index called a rack. With that rack, you can assign this rack to be matching with particular device on your in your computing environment, and that's a non-trivial task. Sometimes you probably want to make sure, for some node we have only 2 devices. When you get the device index, it will only give you 0 and 1. Even if you have 1,000 nodes, if each node has 2 devices, whenever you run it, you'll get 1 and 2, or 0 and 1 on each node. If you really want to communicate with multiple MPI processes, each process needed to understand which particular device it's talking to. And if you are using MPI devices to control only the local devices, what I just mentioned, it should be fine. You just needed to map your MPI process. You give 2 MPI processes to each node. So each MPI process will be matching with one GPU. And then no matter how many nodes you have, your model will be scanning. But in some other special cases, you want your MPI processor to be managing multiple nodes, and you might want to use threads to control the devices, etc. That's getting a bit more messy. But one MPI process, one device, it's probably easy way to get started. And also you want to make sure you all the other separate things about synchronization between devices, etc. So that's something you cannot learn directly by just watching going through the examples I provided, but there are many other online materials you can get into the details about parallel programming with the GPUs. That's like level 2. That's one level about this introductory short course. So there are some extra utility functions you want to use to report the errors, and these errors will be very, very useful for debugging purpose. So CUDA has a long list of error code, and you can go to CUDA library to check out what they are. And this CUDA error_t, it's a special type. It's a function, I believe. Yes, it's a function. It's a type. It's a type defining a different error code. So the CUDA get last error will return this type, and then you can use the CUDA get error string and to print out what the error message is. So I use this a lot for debugging purpose, and you might find this very, very useful for real world programming. And I also mentioned that get a device count, get a device. So you usually get a device count to get the total number of devices you have for a given node. And then you can divide this into multiple processes. You have each process to have a CUDA session device to attach this to the particular MPI process. And then you can get a device and to get the particular device handle, and you can handle that. And also get device properties is a very useful information for you to print out the property for certain devices. If you are working on a homogeneous system, all the GPU devices are the same, and this doesn't matter. But if you are working on a system that, some nodes might be running T4, someone of the T40, some of us might be using A100. And this will be very important for you to decide how you want to divide your tasks so that you load up the balance. You don't want to overload your T4, but give less thing to work on using A100. So you want to give more work on A100 and less on T4, etc. So that's a complicated scenario, but it's a real life scenario. And if you're working in a company, keep upgrading their GPU devices, you probably want to use all the devices available there, right? You might have different generations of GPUs, and you want to use those. But again, all the rest is, managing multiple devices. You can use the threads, you can use the MPI process. And also different devices have different capabilities, and there are some backward compatibility problems. Some devices has a computing capability, certain number, 8, 7, 0, whatever it is, not 0, I'm sorry. It's 11, 10, whatever, it's depending on the generation of your hardware. The hardware is supporting a particular computing capabilities. That computing capabilities will be limiting what you can do with your CUDA code. So that's kind of different from the generation of hardware, but it's following the hardware generation. So the latest generation you have, the higher computing capability you have, etc. So there are more resources coming, and I'll be, I want to acknowledge all the educational materials from NVIDIA Deep Learning Institute. I have been an ambassador from the Deep Learning Institute for multiple years, and it's really helpful for me to get more latest update from the NVIDIA developers and get communicated and synchronized with their programs. And also I get support from TEAS, TAMIDS, and HPRC, and I really appreciate their support in the last several years. And then also this short course is partially supported by the FASTER and ACES grants from SF, and we really appreciate their support. And with that, and that's all. It's perfect timing. Okay, 4 p.m. I know some of you might still want to get back to your FASTER node to practice a bit more. Feel free to modify it. Just trust me, you won't destroy those GPUs. Do whatever you want. Just anything stupid or crazy is fine. Our system has a well protected. Don't be afraid to destroy the system. You won't be able to. So just try to test the boundaries, trying to figure out what you really can do and cannot do. And sometimes you will never know if you are reaching the limit of the thread blocks, and unless you get to some real problems. Try to reach those boundaries as early as you can so that you can avoid those problems in the future when you're starting working on real world problems, right? So that's what these test beds are. That's what faster is, right? Try to use them and try to explore different accelerators in the future, not just CUDA. You know, you might be using FPGA and you might be using different programming scenario, but the basic idea is simple. Decompose the problem, handle each individual task of data point with a very small task, and try to maximize your computing tasks by saturating the hardware, and then using that mechanism to overcome the overhead introduced by data transfer. So that's what CUDA is targeting. That's almost all the other accelerators are aiming for. There will always be overheads when you try to use accelerators. By saturating the hardware, maximize the usage, and then you can overhead those overhead, and you can maximize your computing efficiency. You can speed up your acceleration. Okay, that's all for today. And my email is this. Feel free to contact me. I should be available and happy to answer your questions. And I'll also be following up with some latest version of CUDA 12 because I haven't tried CUDA 12 yet, but I heard there are a lot of fancy things introduced in that newest release. And feel free to reach out if you want to have more information about faster. If I cannot answer your question, I'll get back to our staff members. They will help you to answer your questions. Okay, thank you so much.